Oliver is part of my family, and he married my niece. And we never met because he is based in UK, New Zealand, and I'm based in United States. But he got his education in UK, of course, Cambridge and Durham, and then went to New Zealand to do a PhD in Antarctica glaciology. Can you believe that? Who on earth would have that in mind when you were young? And then he went to postdoc in Burnham Institute in La Jolla, California. And now he works for the British Antarctic exploration team. So I am interested to learn what he's doing, and feel free to ask him for any questions. Or if he can't answer, he can always come back to you. But it's really my pleasure to invite him to join the group and for his own time to tell us what he's doing in Antarctica.
Thank you so much for having me to talk. As Grace has said, I'm Oliver. I'm a glaciologist at the British Antarctic Survey here in Cambridge in the UK. And the work that I do at the moment is all about iceberg formation and the processes that create cracks in ice shelves. So I'm going to talk to you a little bit about that and kind of how we do our work down in Antarctica and some of the new technology that we're using down there to monitor what the ice is doing. So as Grace said, I've been at the British Antarctic Survey for about 7 years. Before that, I did a master's at the University of Cambridge and a PhD in New Zealand. I've spent 10 seasons working down in Antarctica with 3 different Antarctic programs. So as I've moved around studying and doing postdocs, I've been working for different countries' Antarctic programs and at different stations. Most of my current work is from Halley Research Station, which is this one in the bottom left-hand corner. It's quite a futuristic station. It's built on legs and on skis. This helps us to avoid it getting buried and move it around if the dynamics of the ice shelf dictate that we need to move the station. Most of my research is on ice shelf dynamics, so how the ice shelf moves, fracture mechanics, how cracks grow within the ice shelf, ice-ocean interactions, which is mostly about melt rates underneath the ice shelf, and then satellite remote sensing, which kind of ties all this into what's happening on the bigger picture. So I'm going to talk, I'll do a bit of context stuff. I realize this is not what most of your talks are about. Hopefully you're generally familiar with most of this, but I'm going to talk a bit about Antarctic responses to climate. And then I'll talk about how we work at Halley Station, what the Brunt Ice Shelf has been doing, and its recent big calving events, and then covering the technology we use to monitor cracks. So hopefully you're kind of familiar with this. This is a graph of global average temperature going back to 1850 and shows kind of this increase in temperature that we've had for the last 50 or 60 years, particularly warm global average temperatures in 2023 and 2024. And I'm going to quote a few times from the Intergovernmental Panel on Climate Change, which is it's like a United Nations body that collates information from environmental scientists about climate change and gives kind of the facts about what scientists agree on in the state of the climate. And so it's well agreed that there are rapid changes happening in the atmosphere, the ocean, the cryosphere, and the biosphere. And these are leading to adverse impacts on nature and people. And the more we warm the climate, the more likely we are to get abrupt changes or irreversible changes in various aspects of the Earth system. We're trying to limit atmospheric warming to 2 degrees above pre-industrial levels, ideally to 1.5 degrees above pre-industrial levels. We actually exceeded 1.5 degrees in 2024. But it does vary. There's variability from year to year. The way this kind of feeds back on Antarctica and then Antarctica feeds back to kind of our daily lives is through sea level rise. And it's also now agreed that ice sheet and glacier contributions are the dominant source of sea level rise. So there are other things that cause sea level rise, notably thermal expansion. So if you warm up water, it takes up more space, and that is a big component of the sea level rise that we see at the moment. But recently, so in the last couple of decades, the ice sheet and glacier contributions have exceeded that thermal expansion. And this is particularly worrying because it's also accelerating. So the mass lost from Antarctica and Greenland is substantially higher in the last 20 years than it was in the previous 20 years. And these changes may be signs of the onset of a kind of irreversible instability process. And you're probably familiar with tipping points. These aren't just a feature of Earth system processes. So you get tipping points in all kinds of systems. But we know that there are tipping points within the ice sheet, within the Antarctic ice sheet system. So you can imagine this as a ball on a kind of a wiggly, undulating surface. And as you nudge the ball from its stable state towards an unstable state, eventually you would cross a tipping point where it has a positive feedback loop and becomes more unstable and goes back to a different stable state with quite a different configuration to what you started in. So this is one of the primary things that we're trying to understand is where these unstable states are, where these thresholds are, when we're likely to cross them, and what the response will be after we do cross those. We know from data from the past that there are other stable configurations of the Antarctic continent that involve more ice. So back in the last glacial maximum, there was substantially more ice, and a lot of the areas that are currently ice shelves that are floating were resting on the land. We also know from even further in the past, from previous warm periods when CO2 levels were higher than they are today, that we had a much reduced Antarctic ice sheet, also again in a stable configuration. And one of these stable configurations involves an ice loss amount that would create around 6 meters of sea level rise. So the loss of a big part of West Antarctica. And this is generally the process that causes one of these instabilities, this marine ice sheet instability process, it's called, which is where warm water gets in underneath the ice shelves, causes them to melt. This causes the ice to become thin, and this becomes more buoyant. More warm water can get in, it melts more quickly, and it can also flow more quickly. And this is a positive feedback loop that allows you to lose a lot of ice from areas of the continent where the seabed is below sea level. And that's big parts of West Antarctica. So all these dark blue areas on the map on the right here. Okay, so then the last kind of context bit of the talk is about the ice shelves, which is what I'm interested in. These are the bits around the margins of the continent that are already floating. So there's a distinction here between sea ice, which is the frozen surface of the ocean, and the ice shelves, which is ice that used to be on the land that's come down off the land under the weight of gravity and spreads out over the ocean. You only really get ice shelves in Antarctica. There are a few small ice shelves in Greenland, but it needs to be quite cold for an ice shelf to exist. There are substantial ice shelves around Antarctica. The Ross ice shelf is the largest one. But these are particularly important because they're in contact with the warm ocean and with the atmosphere. So they're kind of attacked from both sides. So they're very sensitive to changes in climate. And they also act like a cork, essentially holding back the flow of ice from further inland. So because these ice shelves are already floating, if you move them away, you're not actually changing the displacement of the ocean. What you are doing, though, is removing the force that holds the rest of the ice that's resting on the land back. And we've seen this where we've lost ice shelves in the past, where the glaciers that flow into that area where the ice shelf used to be have accelerated up to 5 or 6 times, and you end up losing all the ice from inland behind where those ice shelves used to be. And we do see big changes in the ice shelves at the moment. So the changes in the ice shelves tend to happen first, and then you get changes in the grounded ice inland. And in particularly in West Antarctica, where we have all these red dots on this figure here. This is where we've got substantial melting and thinning of ice shelves. This is measured using satellite altimetry. So we have satellites that go over Antarctica all the time and record the surface height. So we know a lot of these ice shelves are thinning. Some of these have lost up to 20% of their thickness just in the last couple of decades. And then in other places, we've had complete ice shelf collapse, where ice shelves have been subjected to very warm atmospheric temperatures, causing surface melt ponds to form. And these ponds infiltrate into the ice and help to push cracks apart. So the water pressure basically forces the cracks open, and you can get this kind of rapid disintegration process. So these are all the processes that I'm interested in, these kind of processes that affect ice shelves and the future of the ice shelves around Antarctica. And this makes Halley a good place to work. So Halley is one of the British Antarctic Survey's research stations. This is called Halley 6. So it's the sixth iteration of this research station. Most Antarctic research stations are built on either very slowly moving ice or rock, which is the sensible thing to do so that you don't have to move it and protect it from accumulation. But Halley's on an ice shelf, and this does make it a good place to study ice shelf processes. It's on the Brunt ice shelf. This is an aerial photo of the Brunt ice shelf. So it's kind of a big flat expanse of ice. It's about 200 meters thick. And the station is kind of in the middle here. Yeah, I'm going to show a quick video of how we raise it, how we move the station to avoid it getting buried. Hopefully this works. But essentially these legs are on hydraulics. So to raise one of the modules, so every year we get about 1.5 meters of accumulation. To raise the modules, you need to lift the leg up, you push snow underneath, and then we use these hydraulics to, once we've done all the legs, and then you re-extend the legs and the whole module lifts itself up out of the snow. So this is quite an impressive process to watch, and is quite unique. So here you can see a kind of time lapse of each of the modules being slowly lifted up, which takes about a couple of days, and we do that every season to ensure it doesn't get completely buried by the snow. This station is, we do a number of different types of science at Halley. So there's a lot of atmospheric monitoring. It's got very clean air. This part of Antarctica is difficult to get to, so it's a good place for looking at processes in the atmosphere that are uncontaminated by human activity. And, we look at concentrations of all kinds of gases, including carbon dioxide and methane. We do a lot of space weather research. I say we, this is other scientists who work at the station. So the way the magnetic field works around the Earth, it's a kind of a hotspot for aurora. And we have a lot of instruments that are looking at the magnetosphere and looking at kind of how solar flares interact with the upper atmosphere. Halley was also the location where the ozone hole was confirmed or discovered, one of its claims to fame. So we take ozone measurements daily, and we still do that throughout the summer and the winter. And then we do glaciological research, which is kind of what I'm leading out of Halley. This is a summer team. The summer team is normally around 20 to 30 people. So this is vehicle operators, a doctor, a chef, several scientists. So we usually have a atmospheric scientist, engineers who maintain instruments and various radar systems that look up at the atmosphere. Yeah, mechanics. We have an electrician. Field guides to keep us safe when we're out and about working around the station near cracks, which is essentially what I do. So now I'll talk a bit about the wider ice shelf and what we're using Halley as a base to study in terms of the glaciology. So here it is on the eastern side of the Weddell Sea. It's at 75.5 degrees south. The temperature in the summer is around -5 to -15. So it's not as cold as maybe you might imagine. Probably gets colder in the winter where you guys are. In the winter, it does get down to -50, but generally we're only there in the summer. And at the moment, we use a turbine system to keep the science instruments powered through the winter. And so this is essentially like a jet engine in a box that doesn't require oil changes and services. And so we can run science experiments through the winter. And then when we come back the next summer, we can give it a service. And it's a new way of operating this station that was brought about in 2017 by the appearance of lots of cracks on the ice shelf. So this station was constructed in 2012, and quite soon after, a number of cracks began to form in the ice shelf. The decision was made to move the station to avoid one of those cracks. You can see that process happening down here. So we get a couple of bulldozers and one of these snow piston bully. It's like a snow. This is kind of a machine that you would normally see at a ski resort. To pull the modules to move them out of the way of these cracks. But then essentially we've moved to summer only occupation since then. A lot of these cracks have culminated in large icebergs in 2021, 2023, and 2024. This is an animation from Sentinel-1 satellite imagery of the ice shelf evolving through this period, and you can see the cracks growing, a big piece breaking off, and another piece breaking off here, and then the third carving event here. And Halley Station is in the middle here on this kind of last remaining section. So part of my job is operational based, so informing station management and kind of the operations director about threats to the station and risks to people working there. And so to do this, we need to monitor these cracks, and we need to monitor and understand strain rates within the ice shelf and how the ice shelf is changing. And we do that using a number of different technologies, some of which you're probably reasonably familiar with. So we have a very dense network of dual frequency GNSS instruments. So these are these are like positioning instruments that they run off the GPS network and other countries' equivalents of the GPS network. And they provide very accurate positions of different parts of the ice shelf. So you might think that ice moves quite slowly. Actually, Halley Research Station moves at about 4 meters a day. It's quite a fast-moving ice shelf. It also moves up and down with the ocean tides. So this whole ice shelf is floating. So there's quite a lot of dynamic activity around the station. And we have these kind of GNSS instruments that tell us how the ice shelf is stretching and straining with those tidal processes and the general background velocities. So essentially by differencing positions at each of these sites, we can produce a map of how the ice shelf is stretching and predict how likely it is for cracks to form in new areas that may then kind of become a threat to the station. These sites look a bit like this. So they're kind of an enclosure on some poles that's powered by a solar panel. We bury the batteries because batteries don't like the cold, and it's actually much more of a constant temperature at depth. So the air temperature changes massively between summer and winter, but the temperature of the snow is generally around the annual average temperature, which is about -25. So we want to avoid the batteries getting exposed to these -50 temperatures, which would tend to destroy the batteries. Then we have a UHF mast, which sends the data back to the station. Back at the station, we have a computer which processes this data. So the data collected by these dual frequency GNSS instruments is quite a large volume, and we send it back via an Iridium satellite link. So we want to reduce the data volume as much as we can to reduce the cost of sending that back. So we do some of the processing in an automated way at the station, and then send back information about the strain rates as rather than the raw data. We collect the raw data every summer. This is kind of what the data looks like. So this is a record of velocity at the station. This one goes back to 2013, but we do have data all the way back to the 1950s, not GPS data, but data of velocity. So they used to do these measurements by doing positioning from the stars and various magnetic measurements to work out position. You can see a lot of wiggles in this data. It looks like it might be noise. Actually, this is tidal behavior. And if you zoom in on the latest data, you can see there's quite a strong fortnightly variation in the flow of the ice sheet. So this is related to the spring neap tidal cycles and the fact that ice is a non-Newtonian material, so it behaves in a slightly weird way when you stress it due to ocean tides. But essentially, we can see from this data the response of the ice shelf to big icebergs breaking off. Another instrument that we use that gives very precise measurements of crack width is called a phase-sensitive radar system. So this is actually a system that was designed at BAS to measure melt rates at the base of ice shelves. It has a receiving antenna, a transmitting antenna, and a receiving antenna that here we've mounted on telegraph poles. We've also set up a metal reflector on the other side of the crack. So the crack here is about a hand width wide and goes down the middle between these two parts of the instrument. And then there are cables, and the actual instrument is buried again to protect it from the cold. It's buried with its batteries, and there's an iridium antenna to send the data. But this is an FMCW radar. It's phase sensitive, which means it records very precisely the time it takes for radar waves to travel from the transmitter, bounce off the reflector, and come back to the receiver. And then as the crack widens, we can measure that widening. And it tells us the dynamics of the crack essentially. So this is quite a unique use of this instrument. It is a little bit of a pain to set up. So this reflector is kind of an aluminium, essentially like a dog cage for scary dogs. But it provides a strong reflecting surface that's also not susceptible to the wind too much because it's a mesh essentially. And after a year, it looks like this. So we then have the transmitter and receiver on one side of a big crack and the reflector on the other side. And again, this is after a year of deployment, so coming back to retrieve it and move it the following year. Almost completely buried, so it often involves quite a bit of digging. And actually, most of the work we do down in Antarctica involves a lot of digging. During the COVID affected year, when we couldn't get down for 1 year, we had to leave it for 2 years, and it was incredibly buried, and we had to then find it with a different type of radar because we couldn't see any of the flags on the surface. We had to rope in a bunch of additional diggers from the station to help us dig it out. So this is that same instrument buried about 8 meters underneath the snow. We did manage to retrieve it after about a day of digging, and we got all the data back. So that was very pleasing. This is what that data looks like. It records opening angle of the crack. You can see these wiggles again. These are tidal wiggles associated with how the tides influence the ice shelf and cause the cracks to almost kind of breathe with the tides. And then there's this fortnightly faster rate of widening during spring tides than during neap tides. And I've got a paper that's about to come out about this process that shows how tides can influence the timing of these big calving events. So we've got some of the highest quality data looking at these big ice shelf rifts, and we can look in more detail at the mechanisms involved in what causes icebergs to form. So this again is the tidal data. This orange line shows the height of a GPS system at Halley. So there's these kind of semi-diurnal wiggles with the tide, and then we see the big calving event happened right at the peak of a spring tide, and then the iceberg drifts with the tide after it's separated from the ice shelf. This big calving event, 1,500 square kilometers. I'm trying to think how big that is in terms of. There was a famous iceberg calving event that was likened to the size of Rhode Island. That was about twice this size, so half the size of Rhode Island. This iceberg calving event. And we were there at Halley, so this happened around 10 miles away from the station. We went out and took some drone images of the iceberg drifting away. We did also have GPS instruments on that iceberg, and we can monitor its drift after it's carved, which is what this animation on the right-hand side here shows. And again, you see these tidal variations in the drift of the iceberg. And this is a satellite image from a few days after the calving event happened. And this also shows how some of the area within the crack broke into smaller bits when the calving event happened. So the iceberg itself stays relatively intact. And because this crack was widening for about 10 years before the eventual calving happened, the bit that's widening gets sea ice in it, and then snow falls on top of that sea ice, and you get kind of a a sea icy snow mix in the crack, which is a lot weaker than the ice shelf around the crack. We have other instruments that record iceberg movement. So this is an example. This is kind of a lower profile GPS system. It's called an Adios because it's designed to be air deployable. So in theory, and they have done this previously, you can throw these instruments out of a plane, and they're designed with a pointy tip and a parachute, or like a drogue chute, and a kind of a plate to stop it sinking too much into the snow. But essentially, you can deploy it out of a plane, and it will stick in the snow. Some other tech we use, I won't talk about this too much. We have a number of satellite techniques for monitoring the ice sheet now. Doesn't mean we don't still need to do some ground validation, but I talked previously about altimetry to measure the surface height. You can also measure the widening of various cracks using altimetry because you can see where the height is lower in the middle of the cracks. So this is an example from the Brant Ice Shelf. We have a radar system that can highlight buried crevasses, so features or cracks that you can't see on the surface because they're covered with drifting snow. You can still see using certain frequencies of radar. And there's a paper here about what kind of orientations of satellite data you need to see different types of cracks. So cracks reflect radar waves better if you're kind of looking at them at an angle and you're kind of seeing the flat side of the crack. And if you're looking down the crack, you don't see them very well. Kind of makes sense. We also use radar systems on the ground. This is a GPR sledge that's towed behind a skidoo with a radar on the back. This is a 400 megahertz radar. Snow is actually quite a good conductor of radar waves. You can see quite a long way through the snow, and you can see cracks which appear as these kind of air gaps with hyperbola on either side. So we use these radar to identify features beneath the snow. This is an example of quite a large feature where it's maybe 2 meters wide with about a 2-meter thick bridge. Essentially, as you're driving the radar towards the crack, you start to get a reflection from the crevasse sidewall. When you go over it, there's no reflection at all, it's just air, and then you get a reflection that gradually drops off as you move across the other side. This ice shelf is made of different components, and so the last piece of the puzzle in order to be able to predict when cracks are going to form is to actually understand what the material that makes up the ice shelf is. And so in the last couple of years, we've had a project that's been looking at ice properties, and we've been drilling and collecting ice samples and then bringing them back to Cambridge. And we've been doing fracture tests on the ice in the lab. So we have a shallow drilling system. We set up a drill tent here, and we collect an ice cores, which look a bit like this. We're looking for layers within the ice and the crystal structure of the ice. So we've been working about 40 miles away from Halley at a particular ice crack. So we're drilling around the tip of the crack to look at the properties and how they've been affected by the presence of the crack. We've also been setting up seismic instruments to listen for kind of micro cracks forming in front of the main crack. But what we're primarily interested in is the stress at which, or the stress threshold at which the ice fractures. So this really determines when a crack is going to grow. We know roughly what the stresses are within the ice, but we don't know how strong the ice is, and the ice strength varies substantially from place to place. So this is a kind of a video of us drilling just this last season. You basically can drill about 1 meter at a time, and you pull it up in this barrel and log it. So we're looking at its density in the field. We drilled this year just gone, we drilled 4 holes at about 150 meters deep each. We're looking at physical properties of the ice. Most people who drill ice cores in Antarctica are looking at the chemistry to inform us about the past climate. We're actually looking at the kind of the physics of the ice. So we're interested in the grain size and the crystal structure and things like that. So yeah, here are some examples of kind of ice that we pulled up. So this one in the top, you can see the bubbles within the ice. These do affect its fracture properties. Here you can see kind of cloudy looking ice and quite clear looking ice. This is signs of melt in the past. So where you've had kind of surface melt that's refrozen, and that also affects the fracture properties of the ice. And then this all feeds into a fracture model. So in order to do any predictions of what might happen in the future, you need a model. We do have several models. We have a nice ice sheet model that's quite well established, and we use that to predict how melting is influencing the ice sheet. Incorporating fracture into an ice sheet model is, I mean, it's harder than it sounds, because fracture happens over quite a short time scale in general, and ice behaves over relatively long time scales. So we want to understand how the ice sheet's behaving over decades to centuries, but fracture events happen at kind of speed of sound. You know, it can be very rapid, and so we need a model that can account for this. And we've been developing this kind of phase field approach, which smooths out cracks over a larger kind of area. So you can have a mesh that works with a crack. You don't have to keep remeshing your domain essentially. So these are just some results from our modeling from the moment, which show how as a crack grows and the stress increases, eventually it will break all the way through the ice and you'll get a carving event happen. So we've been developing this model alongside collecting observations, and we're just coming up to the stage where we'll start to apply this model to the Brunt ice shelf to predict how it's going to behave in the future. Yeah, and this is just a last animation from some satellite data of kind of how things have been developing for the last few years. So this is a grounded point on the ice sheet, on the ice shelf, and the ice shelf flows around this, and you can see how as the stress builds up, cracks appear and then it fails. This is essentially the process that we're trying to understand. It's just quite nice to see it in a satellite time sequence. So glaciers do move slowly, but over a period of 10 years, you can see things happening. Yeah, this is just kind of explaining why we see some changes in velocity after the carving events happen. So we're getting this loss of buttressing around this point. Essentially, we have a fixed point on the seabed where the ice shelf is kind of running aground. And then as the stress builds up and cracks form and it weakens around the area, it's not really providing that buttressing anymore, and the ice shelf flows more quickly past it. We published another paper about that in 2024. So what does this mean for the future of the whole area? this is the wider area around the Brunt ice shelf. So the Brunt ice shelf is down here, and Halley Station is down here. This thing up here is the Stancomb ice tongue, and this is at its largest extent that it's been in observed history. So we've had a station on the Brunt ice shelf since the 50s, and this ice tongue hasn't ever been this big since then. There is a chance it was bigger before that. So in 1915, Ernest Shackleton sailed past here and recorded the ice tongue in roughly a similar location to what it is today. So there was probably a big calving event between 1915 and 1957. But since then, there hasn't been one. So it's kind of overdue a big calving event. This will be one of the biggest icebergs that's occurred in the satellite era, so since the 80s. And this is likely to happen within, well, I wouldn't like to make a prediction at this stage until we've run the model for this area, but yeah, this is kind of a thing that we're looking out for into the future. Yeah, so I guess that's all I was going to talk about today. I'm happy to go back over things. I know I kind of tried to talk about a bunch of different things. If you've got any particular questions, it's probably easier just to ask me questions and I can go into more detail that way, though. Thank you.
Thank you, Oliver. It's enlightening to say the least. Any questions here? Yeah, we have one.
So I have a kind of northern hemisphere bias, I guess, in my knowledge of this, but we hear about what happens to big icebergs sometimes that break off and go into the North Atlantic and impact shipping and navigation and stuff like that. But these big Rhode Island size or half Rhode Island size ones that are breaking off, where do they go, and like what's their trajectory in terms of like over years, or do they break up quickly, or do they circle the South Pole, or what's their where do they end up?
Yeah, good question. Yeah, so nearly all of these icebergs travel in the same route. So the southern hemisphere icebergs are somewhat easier to predict their route than the northern hemisphere icebergs. So they go anti-clockwise around the coast of the continent. Quite often they get grounded, so they might run aground on a shallow piece of seabed. But when they reach the Antarctic Peninsula, they can't continue to go anti-clockwise, and the coastal current kind of flings them off into the Southern Ocean. Once they get into the Southern Ocean is quite rough. There's a lot of waves, and it's a few degrees warmer. So they don't tend to last for too long once they're in the Southern Ocean. And it's quite rare to get Antarctic icebergs drifting into areas that are of major concern for shipping. So there have occasionally been large Antarctic icebergs seen off the coast of Cape Town and New Zealand, but it's quite unusual. Yeah, they tend to break up in the Southern Ocean, and then once they've broken up, they have a much bigger surface area, and they're more vulnerable to melting as well.
Great.
There is
Sorry.
currently a very large iceberg that's quite near South Georgia, and it's been threatening kind of penguin populations. So these big icebergs can get grounded in kind of penguin foraging areas, and they can be quite disruptive to ecosystems, depending on their trajectory. But yeah, they're less disruptive for shipping than I think the icebergs that come from Greenland.
Carl?
Yes. First, Oliver, thank you for a very interesting talk. One thing I'm curious about is the sea level rise that is due to melting ice. So you're studying ice shelves, which are already essentially floating, as I understand it, and therefore the calving of that ice shouldn't contribute to sea level rise. Where is the ice coming from that's causing sea level rise?
Yeah, no, that's a good point. So yeah, the ice shelves themselves when they calve, that doesn't change sea level rise. The ice that's causing, so sea level rise at the moment is split into thermal expansion, which makes up just under half, I think, which is just the fact that as you warm the ocean, it takes up more space. Melting alpine glaciers, which is in places like the European Alps, the Andes, Alaska, like these ice caps, they are melting fairly substantially. But in recent years, I think Greenland and Antarctica have begun to overtake. So that's the interior of the Antarctic continent. And that's a response to losing the ice shelves allows the ice that's resting on the land in the interior to move much faster. We're not seeing that around the Brunt Ice Shelf region at the moment, but around Western Antarctica, so places like Thwaites Glacier and Pine Island Glacier, they've seen quite a substantial thinning, so 10 to 20 meters of surface height reduction on the grounded bit, as well as the thinning of the ice shelves. We're also losing mass from the grounded bit there.
Thank you.
Dick?
Yeah, thanks. All right, great talk. I have two questions, if I may. The first one is the formation of ice shelves. My understanding is that much of it comes from movement of ice from the actual land itself out until it's over the ocean. Can you make measurements of how fast these shelves, or say a particular one that you have, is being formed, as opposed to the calving incidents that are going on? Yeah, that's the first question.
Yeah, so this particular ice shelf is slightly unusual in that it doesn't form in the same way as most ice shelves. So most ice shelves, the ice flows across this region we call the grounding zone or the grounding line, which is where it becomes buoyant and basically becomes an ice shelf. There's nothing fundamentally different about the ice that's resting on the land and the ice shelf. It's just a thickness that allows it to float. And yes, there are a lot of measurements of movement of the ice from the interior onto the ice shelves. We do have satellite data so whilst we don't have GPSs in the grounding zone region that often, because it's often quite a crevassed and difficult place to work, we do have very good satellite data from that area. And so we can track features as they move between satellite images to work out the speed of the ice that's kind of replenishing these ice shelves.
The second question is, maybe it's not answerable, but at the beginning of your talk, you talked about tipping points. And I'm curious to know how one assesses when our climate has gotten to a so-called tipping point. In other words, how do you assess that? Can it be assessed so that we know that we're at one or not?
Yeah, I mean, that is a great question. That's a very difficult problem. And it applies to a lot of different tipping points. So I know oceanographers who are interested in there's like an Atlantic, basically the Gulf Stream is another one of these major tipping points where as you freshen the ocean, you can essentially shut down the Gulf Stream and it's very difficult to reverse once you've turned it off. Actually there's two aspects to that. One is knowing the threshold, and two is being able to measure when you've crossed the threshold. For some of these things, we are getting close to being able to know the threshold. Or no, I mean, I guess in different ways we're getting close to either of those. It's rare that we know both of those. So modeling can often tell us what a threshold should be in theory. For things like the Gulf Stream, measuring it, I think, is the difficult bit. For things like the Antarctic kind of marine ice sheet instability, actually understanding what the threshold is also quite difficult. Although I do think there is a route to that, and that is kind of what we're trying to do with this fracture model. So existing ways of representing fracture in ice sheet models are all based on observations, basically saying when the ice gets to this thick, we're going to break it off, or when it reaches this extent, we'll have to get rid of it because it doesn't fit with our observations. It's quite difficult then to extrapolate to a place where you don't have observations, and we think things will behave more quickly in the future, and we don't have good observations of how the ice sheet responds in that case. So what we're trying to do is actually base our model just on the physics of the process and not prescribe any like behavior that's not based on the fundamental properties of the ice and the physics of how ice breaks under stress. So we're going down to kind of the crystal scale to do that. But that should be applicable to any situation, and we can then model how when you lose ice from the front of the ice shelves, if you're left with a cliff that's a kilometer tall, in theory, that shouldn't be able to support itself and would just crumble away, and leave a cliff even higher that would crumble away. And that's another instability theory that we struggle to predict at the moment because we don't have observations of it. So the only way to be able to predict that is to have a model that's based just on the physics. I don't know if that answered your question. I kind of deviated off a little bit there. But
I think you've gotten to kind of my thinking about what's going on with trying to understand climate, because I've always had this thought that we may get to a stable position someplace. As we heat, something will happen and we'll go to stability, because from geological evidence of many centuries ago, Earth was at another place that was much more stable with the temperatures and so forth, bearing the amount of CO2 and so forth around. So I mean, it's just maybe here.
Yeah, no, there will be stable points in the future. It's just whether they're good for humans and ecosystems is a different question. So
Can I ask a question?
Thanks.
Jerry?
I like that. It was a wonderful talk, a kind of a downer, kind of worrisome. But a practical question. When you go to monitor a large crack and you set up your receiver transmitter on one side, your reflector on the other side, how do you get across the crack?
yeah, so we've set up these instruments before the crack gets too wide, where you can just step over it. We are roped up, and we do take precautions when we're working in these crevassed areas. But essentially we link together like mountaineers might do, with harnesses, and we have training in how to rescue someone if they fall down a crack. So it is a bit of a pain when you're setting up science instruments and you're trying to do kind of fiddly things, and you've got all this rope and climbing equipment, and you have to wear a harness. But when more difficult, I would say, is removing the instrument after the crack has become very wide. Then we have to drive around. So we remove one side and then drive around on skidoo and remove the other side.
I mean, you don't have two catapults, one on each side, where they throw the person back and forth?
That would be nice.
Might be interesting. Go ahead, Steve.
On mute.
Working on
There we go.
slow machine. A little mundane questions. When you go down, how long do you spend there at a time?
Yeah, so I'm normally there for about 3 months at a time.
Okay.
Yeah, so it's normally like middle of November till the middle of February, which is kind of the optimum. It's like the warmest time, and it's light all the time, so it's possible to get the work done.
Now, what's it take to get accustomed to the temperature down there? I mean, I guess what I'm asking is, when you're at home right now, you have the air conditioner turned on to bring it down to like 15, so it's used to it, ready for when you go down. How do you get accustomed to the cold?
Yeah, I've got quite used to it because I go quite often. It was actually harder when I lived in New Zealand and would go down. It was in the middle of their summer, so it's always over Christmas is like the only time you can really work down there. So going from London in November when it's kind of cold and miserable, it's not too big of a difference, I guess. And it's actually sometimes more pleasant because you get a lot of sunshine, and when the sun is shining and you're digging, it can get quite hot. But from going from the New Zealand summer into the Antarctic summer was quite a difference. And you have to be prepared with you have to wear all your Antarctic clothing on the plane in case there's a I don't know, in case the plane has to land somewhere different, or for when you get off. And so they used to make us get dressed into our Antarctic clothes before we got on the plane in Christchurch in New Zealand. It'd be like, I don't know, 90 degrees out on the tarmac. So yeah, that can be difficult.
Well, they fly with the windows open, don't they?
We used to go with the New Zealand program and with the US program. We would go on the C-17s, like these big military cargo planes where you kind of sit on the cargo nets at the side. And they also have the Hercules ski planes down there as well. So it's kind of a slow journey.
Oliver, during your presentation, you alluded to the fact that you were able to identify CO2 levels that were much higher than what we had today. Did I hear that correctly?
Yeah, so I think that was a long time in the past. Like, I forget the exact date. So was he going back into the geological era? There were periods when the Antarctic ice sheet wasn't there. Like, if you go back to 30 million years in the past, there's evidence of fossils, and we found fossilized plants and things in Antarctica. But there are periods in history, so we don't have ice core records of that level of CO2 because we don't have ice that's old enough. Although, having said that, ice that is older than any previous ice has recently been acquired, and we are about to process that at BAS. It's not me, but people in our team are looking at ice that may go back to one of the previous interglacials.
So the CO2 levels basically is the conflict with human survival as opposed to the functioning of a planet.
Yeah, so CO2 and temperature are very closely correlated, and in the past it has been a lot warmer than it is today, and CO2 has been much higher. I guess plants do well when it's warm, and you get plants spreading towards the poles, and they create a lot of CO2. Yeah, I think one of the main issues that we have as humans is the fact that we will get large amounts of sea level rise, and it will displace people, and they won't have anywhere to go, and that will cause geopolitical tensions. I mean, there's some countries where there's very little land that's above a few meters above sea level, but somewhere like Bangladesh, there's like 30 million people who live like a meter or two above sea level. If we have all this sea level rise, those people need to go somewhere, which will be problematic. A lot of the big cities in the world are coastal, and it will be very expensive to protect them from sea level rise. So from a sea level rise perspective, which is all I can really talk about, because I'm not an expert on how climate change will affect like local climate. Obviously, we get heat waves, and this is another different problem, and food scarcity. There's a whole range of ways that climate change affects us. Via the Antarctic, it's only really sea level rise.
Yeah. In the United States, they worry about South Florida, but there's lots of people who don't really care about that.
Yeah, unfortunately, the South Floridians will have to move to other places, though.
That could be worse.
Yeah. Bob, you had a question?
Yeah, just briefly related to the coastal changes. There are more serious cases, like there's an entire nation in the Pacific where the islands are going under, and there has been at least one country that has offered them refuge. I believe it was Australia. And now there's some question locally as to whether or not they want Australia's help. So there are political problems that result.
Mm-hmm.
Oh, you can only live on an ark for so long. Shelley?
Yeah, actually, those Pacific islands are growing because they're coral islands. And as the water rises and it gets a little warmer, the coral loves it. So none of those islands, even when the prime minister shows a desk underwater, has actually the islands in fact have grown bigger. They're putting more airplane runways on those islands. Anyway, the Pacific Islands are growing, not shrinking because of the sea level rise. And maybe I have a question. Maybe you can explain the sea level rise from satellites. Satellites show the sea level rise is increasing. Could you tell us about the error bars in the measurements? Because you're measuring, millimeter among 9-foot waves from satellites. How does that work when you have tremendous error bars? That's the part I don't quite understand.
Yeah, I mean, I guess that isn't my area of expertise, but I do know quite a lot about satellite altimetry, which is one of the primary ways that they do measure sea surface heights. So satellite altimetry works on the basis of knowing very accurately where your satellites are and having a good measurement of the time it takes for radar or laser to travel to the sea surface and back. It's a case of averaging over so many measurements over such a long time that we get a very good record. The more measurements you take, the more you reduce your error bars. So that I mean, I can find you some information about that, but it's fairly well agreed amongst the scientific community that the data on sea level rise is quite strong.
Another question I have, are you aware of the latest study that shows very, very high correlation for the last 25 years between reduced cloud cover, therefore reduced albedo, and the temperature rise from 2000 to now, as opposed to CO2? Doesn't correlate with CO2 at all, because there's been an increase in temperature much higher than the rate of CO2. But the lack of clouds with more shortwave radiation hitting the oceans, warming the oceans, is a direct cause of all the temperature gain for 25 years. Are you aware of that new paper?
I don't know which specific paper you're talking about, but there is information about changes in cloud cover in the IPCC report. So the quotes I gave at the start were all related to IPCC reports, which are scientific consensus on what's been happening. And it takes into account cloud cover, and there are uncertainties related to clouds, but they're far smaller than the certainties related to CO2.
Actually, the higher CO2 is supposed to create more clouds. And the fact that we've had less clouds is contrary to the IPCC. And even those that did the study based on satellite data cannot explain why there's a reduction in clouds. That seems to be the million-dollar question today. But the lack of clouds definitely correlates to the increase in temperature. Something else for you to look at.
Yeah, I will have a look, but I would say that anything that is contrary to the IPCC report is wrong, because the IPCC report is heavily peer reviewed by so many scientists, and they do take account of every possible paper and rigorously look into them. So you can always take what's written in the IPCC report as the scientific truth, because it comes with uncertainty estimates and they're very careful about their wording. I agree that there can be new research and new findings that come to light after an IPCC report is published, but they need to be taken, like an individual study needs to be taken with a pinch of salt, based on the massive body of evidence that goes into these big reports.
Thank you.
Thank you.
Bob, go ahead.
Some places there have been reports regarding cloud cover reduction that this may have to do with how industrial pollution has been handled and mishandled by countries like India. It's gone from darker, heavier particulate to lighter colored, lightweight particulate, which does not form raindrops as easily and does not form clouds as easily. Just a little side point.
Also, the reduction of sulfur in diesel fuel for shipping. And there's a thought that sulfur in the air causes cloud aggregation. There could be a lot of reasons.
I am aware of the so yeah, that is definitely a factor. And I think if you look in the IPCC report, you'll see there is a climate reduction associated with there is a temperature reduction associated with cloud cover that is accounted for. I'll try and find you the figure. But yeah.
IPCC does not model clouds very well. I think the grid is 50 kilometers by 50 kilometers, and a thunderstorm might be 2 kilometers by 2 kilometers. They really cannot, they really don't factor, none of the models really factor clouds, thunderstorms, and stuff like that. It's more guesswork than real modeling. The grids are too big.
The IPCC doesn't do any research of its own. It just aggregates research from scientists all around the world. So it just takes the best possible papers and research that is available and looks at it all as like a big sweep.
They do leave out some researchers like Lindzen. They pick and choose which researchers they put in, especially in the last few. They don't like certain researchers, so they leave them out. It's just the way it is.
Dick?
Yeah, quick question. How much data do we have about the H2O levels in the atmosphere in terms of how it affects climate? In other words, not just clouds, but H2O as a gas, because CO2, methane, other gases have been implicated as causing climate change. And I've always wondered about how much research has been done on the H2O, because there's a lot of H2O in the atmosphere compared to other gases.
Mm-hmm. Yeah, I mean, I think it is a greenhouse gas. I don't know, to be honest. I would have to go and look that up.
Exactly.
It's the biggest greenhouse gas, by the way.
I would
because
think so.
it has the biggest spectrum
Yep.
of red, the infrared. It's
Right.
the biggest one.
That's when I first did calculations on this stuff, when this stuff was happening 5 or 10 years ago. I said, well, what about H2O? So I went back and looked at the spectrum. Yeah, I saw the same thing.
Mm-hmm.
And I wondered why we're not looking at that.
Yes. Oh, I believe we are looking at it, and it's believed to be an amplifying factor, but not an originating factor.
Mm-hmm.
So when the atmosphere warms, there's more H2O in the atmosphere. So that tends to increase the effect of other greenhouse gases.
Yeah, so what's happening, I mean, the way we're looking at climate change is the fact that we're changing the gases that are in there, like the CO2 emissions, sulfur emissions, methane emissions. Whereas the water, we're not changing it that much, and it's reacting to the fact other things have caused the change. Okay. Sounds
Actually, the increase in infrared in short wavelengths the last 25 years that warms the ocean and helps the ocean level rise because of expansion also pushes the CO2 out of the ocean into the air. So the man-made portion of the CO2 in the air is much smaller than the natural. In fact, a new study just came out, brand new study just came out that says that rivers and streams take old gasoline-based CO2, old CO2 from the rocks and push it into the ocean. So all the CO2 that people thought because of radiocarbon dating were just man-made actually comes from the rocks on the earth through the streams. So again, a brand new study that's this year that shows that the man-made CO2 based on radiocarbon, it's not accurate. It's only half, because the other half comes from streams out of rocks and limestone and everything else. A lot of new studies have come out recently.
Shelley, just there's a gap here. If you look back, we had a talk by Michael Perlman from the Smithsonian about the geodesy and the space measurements of wave heights and things like that. You may want to look at that video and of that it was recorded here. You may want to look at that and understand how some of that's done, and may answer your questions about errors and what have you.
Sure, thank you.
Any other questions?
I've got one. If
We got one here.
yeah, is there anything to be taken seriously in terms of use of these large icebergs as resources for fresh water?
Yeah,
that's
there has been some research onto this previously. So there've been like groups who got together to decide, is this a opportunity? Places like Cape Town that have massive water issues, like shortage of water, have looked into this fairly seriously. It's never seemed to be economically feasible. Partially because once you drag these icebergs to places where water is needed, then they melt very quickly, and you're going to get much less water out of them than you had hoped. Or you can try and protect them as you drag them, but that would require like a big net. I mean, there has been research done, and it's never been quite over that threshold to make it a viable thing to do. It does keep coming up as a possibility, but personally I think it is unlikely to make sense unless an iceberg happens to drift very near to a place, and icebergs have been seen couple of 100 kilometers off the coast of Cape Town, and in that case maybe you could make use of it somehow, but in general, no, I don't think that's feasible.
I have one last question. I know over the last 20, 25 years, the sea ice has been melting around Antarctica, but the last 2 years, what I've just read is that sea ice has been growing for whatever reason. And I'm just wondering if your studies detect, additional sea ice and how, if that helps stabilize some of the ice shelves.
As far as I know, sea ice was at an all-time low last year, and previous all-time low the year before. I think sea ice is at historical minima. So there was a period where it didn't appear that sea ice was decreasing very rapidly in Antarctica, but more recently it has decreased quite quickly. We do see that sea ice may have an effect on stabilizing ice shelves, as in some ice shelves where you get sea ice out the front, you don't get as much calving, and you get calving preferentially in the summer months when the sea ice disappears. Okay. Antarctica has massive seasonal variability in sea ice, as in the sea ice essentially doubles the area of the continent in the winter, and then pretty much all recedes back, and there's very little sea ice in the summer anyway in Antarctica. Okay. Yeah, but yeah, I think the impact of sea ice on ice shelves is still a little bit up for debate, as in it's quite a thin layer and it shouldn't have that much support for the ice shelves, but there's observational evidence that suggests in some places it does restrict calving when it's there, and then when it disappears you get more calving events happening.
Thanks.
Question: if you drill down in the land ice, does it get colder or warmer the deeper you go?
That's a good question. That depends where you are in the continent. So on the ice shelves, it tends to get, in the summer it gets colder until you get to about 10 meters, and then it gets warmer as you go down towards the ocean, because the base of the ice shelf is the same temperature as the ocean, which is about -2. On the grounded ice, in some places you have melting at the base. So in areas that are moving quickly, you get water at the base of the ice sheet that helps it to slide and helps it to move. And in those places, you've also got temperatures of about 0 at the base. So you'd get it getting warmer as you got near the base. You can also get geothermal heat that helps to warm the base. Some places it's frozen to the bed, and then the temperature profile will be slightly flatter. It's always going to be quite cold near the surface because that's where the very cold air temperatures are.
Yeah, the ice skate effect.
Cascade effect.
And that's actually correct. You know, the pressure and the geothermal warming between the two will actually melt, you know, a small portion of the ice at the base of the iceberg. Is that a fair statement?
Yeah, yeah, the pressure, so pressure is a big factor in causing lubrication and then also friction. Once you get ice that's moving and sliding over the bed, you generate frictional heating as well. So there are various ways to get heat to the bed, but it's very difficult to dissipate heat away from the bed because ice is a very good insulator. So yeah.
So your next PhD will be how to drill down and put thermal radiators at the base of icebergs to keep them frozen so that the ice doesn't move.
I mean, there's a lot of work at the moment on these kind of geoengineering type schemes. It's quite popular in a way, but in general, in most cases, it's not very feasible. So a lot of these plans to kind of build walls around the continent to stop warm water getting in, and to kind of seed clouds to help it snow more. You know, there's a lot of research being done into whether these things are likely to work, but the scale and the costs are just enormous. That the easiest thing to do is just to stop emitting greenhouse gases to avoid these negative consequences. Yep.
Well, the fact of the matter is, I mean, you know, just with cost, even the programs that you work with, those are not inexpensive studies. That, you know, somebody's paying a fair amount of money to keep you guys going, and that's not necessarily a bad thing. I'm not criticizing it. I'm talking in absolute dollars. There's a lot of money going to keeping the research stations on Antarctica alive and going, funding your research and everybody else is doing research.
Mm-hmm. Yeah, no, exactly. I mean, it's not easy to get to this station, and because of where it is, it's difficult to maintain the station. I mean, we have to raise it up every year, as I showed you. One of the good things about this particular station is because the station supports all this other science. And one of the big things we support is space weather forecasting, which has a big kind of commercial aspect to it. So satellite operators for communication satellites and various other satellites want to protect their satellites because satellites are expensive to launch. And so they want to know when like geomagnetic storms and things are forecast. And so some of the data we provide that only we can provide because we're the only location within, 800 miles of, to get a good forecast, you need a dense grid of observations, and you need observations in particular places, particularly where there's no other observations nearby. So some of the other observations that we provide are good to like justify our presence there. And the fact that we are present there means we need to monitor that particular ice shelf. And the fact that we need to monitor that ice shelf means we can learn all about fracture processes. So because it's difficult to get long-term monitoring studies funded, but because we have to monitor the ice shelf for operational reasons, we can use that long-term data to understand processes that we wouldn't otherwise know very much about.
Great elevator speech. Well done.
Thanks.
Any other questions? Go ahead.
So again, reflecting US bias here, but we've been hearing a lot, probably more about Greenland in the last year than for the combined 50 years prior to that. But could you kind of give a general comment about the applicability of the concepts and research that you're looking at to the Greenland ice sheet? I know the melting of the ice on Greenland? I know there's a slightly different set of mechanics at work there, but could you comment on that?
Yeah, so I haven't done much work in Greenland, but I do know quite a lot about the Greenland ice sheet. So the Greenland ice sheet doesn't have many ice shelves. So a lot of the carving processes that we're talking about are not like directly applicable, but it does have outlet glaciers which terminate in oceans. So you may see these videos of big carving events and very messy looking ice where big blocks roll over. And those kind of fracture processes are still the same processes that we're trying to model. So the ice that we are working on in the lab and the way crystal orientation and things affects fracture, that's still the same process that's happening in Greenland. It's just the fracture. They're not rifts growing horizontally through an ice shelf. They're cracks growing vertically that then kind of create crumbly ice cliffs. The main difference between Antarctica and Greenland is Greenland gets substantially warmer air temperatures, and so they have much higher rates of surface melting. And so if you see pictures of kind of streams and big ponds on the surface of ice sheets, most of those are from Greenland. And a lot of the glaciologists who work in Greenland are interested in glacier hydrology, so how water interacts with the ice to create slippery beds that allow the ice to flow, and kind of feedbacks between surface melting and rates of ice loss. So the ice is not just lost through the surface melting, it's also lost through the meltwater getting to the bed and allowing the ice to flow more quickly. So yeah, I mean there are parallels, but there are differences in that Antarctica doesn't have that much surface melting and doesn't have that much these kind of big lake drainage events and things.
So you could kind of get the impression for Greenland that in a scale of decades that like more of Greenland will go from being covered by ice sheets to being completely uncovered. I get the sense that that's very far from happening anywhere in Antarctica. Is that a correct understanding?
I may not be right here, but I think Greenland is currently contributing more to sea level rise than Antarctica. Antarctica has much greater potential for very rapid rates. So essentially, Greenland doesn't have as many of these instability mechanisms where you can get massive amounts of loss. One of the biggest kind of tipping points in Greenland is as you melt the ice sheet and reduce its surface height, the temperature at the surface increases because the lower you are, the warmer it is. So that's an instability mechanism. And that also exists for Antarctica. But this kind of marine ice sheet instability that I talked about, where your ice is resting on land that's below sea level and the ocean can get in and melt, that isn't really a process in Greenland. So because ocean water has a much bigger thermal capacity than air, it's possible to lose ice much more quickly if you have warm water doing the melting than if you have warm air. So whilst Greenland is a big contributor at the moment and will continue to increase, Antarctica will likely increase very rapidly at some point, and we're trying to work out when that will be.
Oliver, thank you very much. One last comment, just a thought for you. I was reading somewhere that a long time ago, they learned how to transport ice by putting sawdust around it. You think that's viable for Antarctica?
Yeah, lots of trees down there, don't they?
Well, maybe before, maybe when the forest was there, that was what they happened. They used it all up.
That was before the Joule Thompson effect was understood.
Were they trying to make aircraft carriers or something? I seem to remember reading.
Yeah, something like that. Well, thank you very much. It's late in your day, and we appreciate your time and making some time for us. And thank you, Grace, for bringing this to us.
You're very welcome. I enjoyed it.
That's great.
No problem. Thank you very much.